All right, so this problem is asking us, this is number 8, if 1.7 times 10 to the third grams of aluminum hydroxide are combined with 680 grams of sulfuric acid, how much aluminum sulfate can form? So what we want to know is we want to know what products are going to form out of this reaction. And we also want to know uh, what our limiting reagent is going to be, because if we can figure out our limiting reagent, then we know that the product is going to depend, the amount of product form is going to depend on that limiting reagent. So let's look at the reactants here. So I underlined these for reference. If we look at this, we have aluminum hydroxide. That's a very strong base. Strong bases, are very, very low alkalinity. And then likewise with acids, this is a sulfuric acid. It's a very strong acid. So it's different. The pH level uh, is, it's got a higher pH level. And I didn't mean to say lower alkalinity. I meant to say lower pH. So, acids like on the other side of the spectrum. So because of that, when we put the two together, they're going to neutralize one another and they're going to create water. So we know water is already going to be a product. Well, if we think about when we add these two together, we're going to obviously have to balance this equation. So let me go ahead and first write out what is going to form as products. So we know we're going to have aluminum hydroxide. We're going to have sulfuric acid. We know we're going to have H2O formed because water is a product of neutralizations. And it says right here aluminum sulfate. So we already know we're going to be given aluminum sulfate as well. And the formula for aluminum sulfate is Al2OA, or I'm sorry, not OH, sorry. Let's go back to that. It's going to be SO2 SO4 3, because based on the charge of these elements. Now let's think about the states in which these are in. Aluminum hydroxide is actually a solid. It's not aqueous, and we can refer to our solubility charts. Any hydroxide is always going to be insoluble with an exception of a few things. If you're mixing it with or if it's combined with a group 1 metal such as sodium or potassium, that is going to allow it to be soluble. And then of course there's ammonia, and I want to say, let me see here, aluminum. I'm not aluminum. Let's see. So ammonia, calcium, barium, or silicon, those will actually cause it to be aqueous. However, aluminum is not included in that list, so we can say that this is a solid. Now, if we look at sulfuric acid, sulfates are always soluble with exception of certain metals, but hydrogen is not a metal, so we can say that this is aqueous. And likewise with aluminum sulfate, same case. Certain metals that qualify to make this that make it a precipitate. However, we don't have, aluminum's not one of those metals, so we can say that this is an aqueous. And with H2O, the current state of that is it's just going to be a liquid form. So this is what we're going to get when we put these together. So now the next thing we want to do is we want to determine the balance of the equation, because we are not balanced. Normally what I suggest is ignore the oxygens till last, because if you think about it, oxygen is in every single term. Let's look at aluminum first. If we look at the aluminum on the right-hand side, I've got 2 aluminums in my aluminum sulfate, but I've only got 1 in my aluminum hydroxide. So I know I'm going to have 2 aluminums. So actually, let me just do this. So I know I'm going to have 2 aluminums. Okay, and now if I look at my, if I pay attention to my hydrogens, what do I get? So on my hydrogen side here, I've got 3 hydrogens times 2 is going to give me 6 hydrogens, plus another 2 hydrogens, which is going to give me a total of 8 on the left. How about on the right? On the right, I've only got 2 hydrogens, so that's going to be 2. So instead, what I could do is I can just make this a 4 for H2O here. So then I'm going to be left with 8 hydrogens. Okay, so we got that balanced. But how about oxygens? What does that do to my oxygens? Now, if I look at my oxygens here, actually, we'll look at sulfur. Actually, what I'm doing is I'm treating sulfate as if it's one thing, but now I'm just breaking it up. So let me look at oxygens next. Even though I said leave oxygen for last, because I have oxygen inside this first term here, I'm going to work with that one first. So if I look at my oxygens here, I'm going to have let's see, 3 times 2 is 6 oxygens, and then I've got 4 more here, which is going to give me 10. And on the right-hand side, I've got 4 here, and then I've got 12 here. That's going to give me a total. So I have a higher unit here of 12 compared to the 10 over here. So I need to get 2 more oxygens at least in order to get the proper balance for this to create a balance for my oxygen. So what can I do? Well, I could make this a 3. And what happens when I put a 3 here? Well, of course, this is going to change my hydrogens, but by what factor? So let's think about this. If I do this now, let's look at my oxygens again. I'm going to have 6 oxygens on the left on my first term. Then I'm going to have 4 oxygens times 3, which is going to give me 12. So that's going to give me a total of 18. And on the right, I've got 4 oxygens plus another 12 oxygens. That's going to give me 16. Okay, so I'm still 2 off, but what I can do is I can just take this 4 now and turn it into a 6. And in doing so, I'm going to have 6 oxygens plus another 12 oxygens gives me 18 oxygens. So now my oxygens are balanced. But of course, I have to keep in mind now with my hydrogens to see if those are still matched. So let's look at my hydrogens again. Hydrogens, I've got 6 on the first term, plus another 6 gives me 12. And on this side, hydrogens, I've got 6 times 2, that's 12. So those are balanced. Aluminum stayed the same. I didn't affect any of the aluminum changes. And lastly, let's look at our sulfur. Sulfur, I've got 3 here. And over here, I've got 3. So this right here is a balanced equation. I know it may seem a little unorthodox, but this is a proper way to balance. So now that we've got our balance, we can do the next step. We can find molar masses. We're going to need to find molar masses of our reactants in order to determine the product. So if I do molar mass, let's do the molar mass first of aluminum hydroxide. I found that I did a little bit of calculating here, and that's going to become 78 grams per mole. And you can find that by taking, the mass of aluminum. So you can take the mass of aluminum plus 3 times the mass of oxygen plus another 3 times the mass of hydrogen. And what that's going to give you is going to be 78 grams per mole. Okay, and then likewise, we can do the same thing for sulfuric acid. The molar mass for sulfuric acid is found by doing the same thing. And the molar mass for that's going to come out to be 98.08 grams per mole. So now that I've got these, so this is my aluminum hydroxide, and this is my sulfuric acid. Now I can check to see which one of these is my limiting reagent, and by doing that, then that limiting reagent I can compare that to my aluminum sulfate, and when I do that, that's going to be able to tell me exactly how much aluminum sulfate I'm able to create or form based off the given amounts in this reaction. So let's start with aluminum hydroxide. Let's just find out exactly how many grams of aluminum sulfate can be created from the provided amount of aluminum hydroxide. So I had 1.7 times 10 to the 3 grams of aluminum hydroxide. And I'm going to multiply that by 1 mole because I want to do a mole ratio of the two, the product and the reactant. So 1 mole of AlOH3 is equivalent to 78 grams of AlOH3. And then I want to multiply that by the molar ratio. So if we look at our balanced equation here, I have 2 moles of aluminum hydroxide, and that creates 1 mole of aluminum sulfate. So we know that we're going to have 1 mole aluminum sulfate. And then on the bottom here, I'm going to have 2 moles of aluminum hydroxide. And lastly, we do need to find molar mass of aluminum sulfate. I did find that as well. And what I found that to be was I calculated that based off of the doing the same method that I did for the reactants, and that's going to become 340, not 47, that's 42 grams, 0.15 grams per mole. So I'm going to multiply that as well because I want to get this in terms of grams. So I'm going to have 342.15 grams of aluminum sulfate per mole of aluminum sulfate. Okay, so when we calculate all this together, we see that our grams of aluminum hydroxide are going to go away. The moles of aluminum hydroxide are going to go away. And the moles of aluminum sulfate are going to go away, leaving us with just the grams of aluminum sulfate. And when we calculate all this together here, we're going to have this divided by 7, also divided by 2, and then multiplied by this molar mass. I'm going to get a value of 3.7 times 10 to the third grams of aluminum sulfate produced when provided with this much of aluminum hydroxide. Okay, so what I'm going to do is I'm going to erase this bit. I'm going to save that value down there, and we're going to do the same thing now for sulfuric acid based on the given amount, which was 680 grams, and we're going to see if that value is going to be larger or smaller than what the aluminum hydroxide can provide. So what I'll do here is I'm going to start with 680 grams of sulfuric acid. Okay, and again, we're going to multiply that by its mole. Okay, so we know that 1 mole of sulfuric acid is going to be equivalent to, what do we say, 98.08 grams of H2SO4. Let's multiply that by the mole ratio. And again, now I have for every 3 moles of sulfuric acid in the reaction, 1 mole of aluminum sulfate is going to be created. So we'll have 1 mole of aluminum sulfate multiplied, and then divide that by the molar ratio of the moles of sulfuric acid in this example. And lastly, like we did in the last part, we're going to multiply this again by its molar mass because we want to get this in terms of grams. So we know that 1 mole of Al2SO43 is going to be equivalent to 342 grams per mole. All right, so again, same process as we did for the first term. So we're going to cancel out grams of H2SO4, we're going to cancel out moles of H2SO4, and we're going to cancel out moles of aluminum sulfate. And when we calculate all this together, we get a value of 790.73 grams. So clearly, by looking at this comparison, we can see that the limiting reagent is, of course, the smaller the values, and clearly sulfuric acid is going to produce much less with its availability than that of aluminum hydroxide. So our limiting reagent in this case is going to equal sulfuric acid. And luckily for us, we just found the answer to this problem because we wanted to calculate how much of this can be produced. And we've now seen that we can produce exactly 790.73 grams of aluminum sulfate based on being given 680 grams to start with. So this right here is going to be the final answer. We weren't asked to find the limiting reagent. However, finding the limiting reagent was critical in order to get this problem correct.